Finding the volume of a solid of revolution using the washer method. Now, we talked about the disk method in the previous video, and remember when I said the disk method, I was talking about something that would look like a compact disk. And now we're going to be doing the washer method, and I don't mean a washing machine, folks. I mean one of these tiny little washer things that you could buy at the hardware store. So my first question to you is, what if I had a situation like this? It's just a rectangle, and I want to rotate this rectangle about the x-axis, so 360 degrees about the x-axis. What three-dimensional shape would be created? And now we're back with Autograph software, and I have the line y equals 5 there in red and the line y equals 1 in blue. First, I'm going to find the area between these curves. I'm going to sort of recreate that rectangle we were just looking about. So I'm going to select each curve. I'm going to choose Create Area. We're going to go from 1 to 3, like so. And there's my rectangle. And again, I want to know what three-dimensional shape am I going to get when I rotate this rectangle about the x-axis. I'm going to select it. Try again. Select, create, volume, y equals 0. Here we go. Whoa, it looks a little bit like a disc. Uh-oh, but there's a hole in it. You can look right down in the middle of that hole. Folks, that's not a disc anymore. That is a washer, hence the washer method. Now, how could I find the volume of this particular washer, or it basically is a cylinder with a hole in it, a hollow cylinder? Well, if you said that you would find the volume of the larger cylinder, the outermost cylinder, and then subtract the volume of the hollow cylinder, you would be correct. So let's take a look at this situation. I have here a parabola and a line, and I want to find first the area between these two curves. So I select them, create area. They intersect at 0, and they intersect again when x is equal to 8. So I'm just going to find that area that's bounded by those two curves. Now I'm going to take that area, and I'm going to rotate it around the line y equals 0. And let's have a look. Oh, wait, let me turn the turtle back on so we can watch it. It's really fun to watch. Create, volume, okay. Ooh, this is really beautiful. It looks really modern. It looks like it could have been, I don't know, a vase that would not stand up because it's a point on the one end. Anyway, it's a rather attractive shape, and we might want to find the volume of that shape. How would we do that? Well, let's back up a bit. Remember when we were finding the area here, I just used this fancy method in the software. But what if I were to choose right rectangles and I were to say that I wanted 8 divisions? I would have these little rectangles here, and let's take those rectangles and rotate them around the y equals 0. And we are going to get a series of washers. Look at that, a series of washers. That the volume of the sum of the volumes of these washers, let me say that again. The sum of the volumes of all these washers is obviously not going to be the same as the volume of that beautiful shape that we're looking at before, but it gives you an estimate. And of course, I can do more rectangles, which would create more washers. I think you see where I'm going here. Let's turn off the turtle and just go ahead and I thought I did. Okay. Sorry. Right click, create, volume. There we go. Okay. So yeah, more rectangles would give me more washers, and then that would make it a more accurate volume. And so just like with the disk method, we actually want an infinite number of washers that are infinitely thin. And then we can add all those up, and we use calculus and specifically an integral to do so. So this slide has a side-by-side comparison of the disk method versus the washer method. So in the previous video, we talked about the disk method, and it's just a very thin cylinder, which we call a disk, where the height is on its side, and it looks like a communion wafer, if you will. And you would add up an infinite number of those that are infinitely thin, and you get the volume of this shape here. That would be rotated around. Now, the washer method is the same idea. The difference is that we now have a hole in our cylinder, and so we're going to call it a washer. So let me remind you that the height of the cylinder is there. That's the height of the cylinder. And we're going to call that, though, dx because it's going to be the change in the x. And then when you're looking at this cylinder, this hollow cylinder, you're going to have this radius here from the axis of rotation all the way out to the edge. We're going to call that big R. And then we're going to have another radius of the hollow part. That's going to be little r. So I'm going to talk more about that in the next slide. So let's go back to geometry class, remind ourselves how we can find the volume of a hollow cylinder. So here's a cylinder drawn. The radius of the outer cylinder is big R. The radius of the inner cylinder, which is your hollow part, is little r. And the height, of course, is h. So this is the formula for volume of a cylinder from geometry class. So for this particular hollow cylinder, it would be pi r squared h minus pi, I should have said pi big R squared h minus pi little r squared h. So let's relate that to the calculus now. So let's say that we had this area here between these two curves. We've got a line and then a curve here. And we're going to take like one little rectangle like so, and you're going to rotate it around this horizontal line here, which would be its axis of rotation. And you get a shape that looks like that. It looks like a lampshade to me. So the way that it works is the radius of the outermost cylinder is big R of x. So that's just going to be whatever your outermost function is, and then little r of x would be the distance between the axis of rotation and axis of revolution to the bottom of that rectangle there. And so we have this. We're looking at pi times the integral from a to b of big R of x squared dx. Remember, the dx is like the height of your cylinder, minus pi, the integral from a to b of little r of x squared dx. So again, we're looking at the outermost radius minus the innermost radius. So the outermost function minus the innermost function. So that's the volume of the entire solid, and that would be the volume of the whole. And then this is not the formula because you can simplify this with your properties of definite integrals and get that. So that is the formula that you should write down for the washer method. Pi times the integral from a to b of the big R of x squared, that's going to be your outermost function, and then the minus little r of x squared, that's your innermost function. And that's going to give you the volume of the solid using the washer method. Let's take a look at example 1. All right, so they want us to find the volume of the solid generated when you rotate the region that's bounded by this quadratic function and just the line y equals x over this interval from 0 to 2, and you revolve that around the x-axis. So they've included the diagram here. You can see the parabola, and then you've got a line, and then they just sort of chopped it off right here at x equals 2 and at x equals 0. So for the volume, using the washer method, we're going to do pi times the integral from 0 to 2 of the upper function, which is the parabola, so 1/2 plus x squared minus the just x squared, close square bracket, dx. All right, now I'm going to do most of this in my calculator. So if I do like all of this bit in my calculator, then I'm going to end up getting 69/10. So pi times 69 over 10. So we can just call that 69 pi over 10, which is approximately 21.677. Now, with regards to the calculator, what I would recommend that you do is call this function, the quadratic function, call that one y1 or type it into y1 into your calculator. And then in y2, you're just going to type x, right? Just y equals x. So then in your calculator, my son is making noises in the background. You can probably hear it. In your calculator, you're going to do pi times the integral from 0 to 2 of y1 squared minus y2 squared dx. And that, if you include the pi, that's going to end up giving you that decimal. If you don't include the pi, you're just going to get the 69/10. Let's take a look at example 2. So similar thing, we want to find the volume of the solid that's formed when we revolve this region that's bounded by y equals the square root of x and y equals x squared about the x-axis. They just don't give us the graph this time. So what you're going to want to do first is get a visual of what it looks like. So the graph, the square root of x is like half of a sideways parabola like that. So that's y equals the square root of x. And then the graph y equals x squared, of course, is just a normal upward opening parabola. So we're going to go over here. So something like that. That's y equals x squared. And so you want to find the region that's bounded, or you want to take this region that's bounded by these two curves, and then you're going to rotate it around the x-axis like so. So what you're going to need to find, of course, first is your intersection points, so that you know what your lower intersection points, what your lower bound and your upper bound are. These graphs are not too difficult. Hopefully you can figure out that they intersect at the origin, and then they also intersect at 1, 1. If you're not sure about that, feel free to graph them in your calculator and find those points of intersection. So when we want to find the volume, using the disk method, we're going to do pi times the integral from 0 to 1. Remember, for your bounds, you're always looking only at the x coordinates from 0 to 1 there. And then you're going to do the upper function, which is the square root of x, and then you're going to square it, minus the lower function, which is x squared, and you're going to square that one, dx. And so when you work that out in your calculator, if you just do the integral bit, you're going to have pi times 3 over 10, which is 3 pi over 10, which is about 0.942. So I would accept either one of these things, like 3 pi over 10 or 0.942. And of course, in the calculator, okay, my son is laughing. It's awesome. Now, if you were doing this in your calculator, what you could do is you could call this first function y1. You type that into y1, the square root of x, and then in y2, just type in the x squared. Remember, don't square the functions when you're typing them into y1, y2. Type them in the way that they're given in the question. And so then in your calculator, from the home screen, you can do that math9 command. So you'll do pi times the integral from 0 to 1 of y1 squared minus y2 squared dx. And if you don't include the pi, then you're going to end up getting the 3 pi over 10. If you do multiply then by pi, you'll get the 0.942. Down here is the graphs of these functions, a very nice diagram of the graphs of these functions here. And then they also have here included what that shape looks like when you revolve it. So sort of this nice little, like a bowl looking shape. I kind of like it. All right, now let's try example 3. So similar kind of thing. We've got the function y equals 2x squared, and then just y equals 8 and the y-axis. So this is a little different. So let's do a visual. Let's graph these functions. So y equals x squared, 2x squared, excuse me, is going to be a parabola. It's going to be a little bit thinner because of that. It's kind of that vertical stretch there with the 2 in the front. So something like that, like y equals 2x squared. And then the function y equals 8, of course, that's just a horizontal line. So that's the function y equals 8. And then you also are talking about bounding about the y-axis there. And the reason that they mention the y-axis, because you can see that you've got this region and this region are bounded by those two curves. So that's why they're also asking for bounded by the y-axis. And in fact, it doesn't matter if you do this region on the left or the region on the right, because those are going to be the same volume when you rotate them, because of the symmetry. In this particular case, it's not always the case if it's not symmetric. But at any rate, we're going to take one of these regions that's bounded by the y-axis and these two curves, and we're going to rotate it about the x-axis again. We're going to indicate our axis of rotation with a little arrow like that. And so we also need to find the points of intersection for our lower bound and our upper bound. The lower bound, well, those intersect the y-axis and the parabola intersect at 0, 0. And for the upper bound, we're looking at this point of intersection for the y equals 8 and the 2x squared. You could easily find that with algebra by just setting those two functions equal to each other. 8 equals 2x squared, 4 equals x squared, plus or minus 2 is equal to x. So this is going to be 2, 8. And of course, this other point of intersection over there is the negative 2, 8, but we're not concerned about that. So for our volume integral, we're going to say pi times integral from 0 to 2 of the upper function, which is 8, squared, have to square the function, minus the lower function, 2x squared, squared dx. And you can put some extra square brackets like so. And then when you do that in your calculator, you'll get 512 pi over 5, which is about equal to 321.699. And that is the volume of that solid when you rotate it around the x-axis. So at this stage, you're probably saying to yourself, how do you know when to use the disk method and when to use the washer method? Well, it depends on the situation. So here is a diagram, 2 diagrams to show you the difference between the disk method and the washer method. So the disk method is going to happen whenever, remember, it's all about rectangles that you're going to rotate around the axis of rotation, or here they're called the axis of revolution, and those are going to create cylinders. If your cylinder is not going to be hollow, we call it a disk. If your cylinder is going to be hollow, then we call it a washer. So this cylinder, since this particular rectangle borders the axis of rotation or the axis of revolution, then it's not going to be a hollow cylinder when you rotate it, and so you use the disk method. This rectangle does not border the axis of revolution, which again, you can see they're indicating it down there as the x-axis. And so when you rotate this particular rectangle, you will have a hollow cylinder, which we call a washer. So that's how you tell the difference between the two, the disk method and the washer method. If your region is bounded by the axis of revolution or the axis of rotation, then it's the disk method. If there's going to gap between your area, that region, and the axis of revolution, then it's going to end up being the washer method, and you have to do the upper function minus the lower function. The truth is, the disk method is just a special case of the washer method where your lower function is just 0. Your lower or your smaller radius is just 0.